Hi, so my name is Roy Schwartz, and I'm here to tell you about green AI. Sorry, let me just call this. Okay, so before I begin, I'd like to say just a few words about myself. I'm a senior lecturer at the School of Computer Science at the Hebrew University of Jerusalem. I study artificial intelligence with a focus on natural language processing, or NLP. And my main goals in studying these topics is to get, on the one hand, a better understanding of AI models, and on the other hand, understand the data sets on which they are trained and uncover biases that exist in them. And finally, and most related to this session, one of the things that I'm most interested about is how to make AI more sustainable. And this will be the main focus of this talk. Okay, so when we think about AI today, we think of a technology that has improved the state of the art in a wide range of fields, going from beating world champions in games like Go to allowing us to get great performance in tasks like machine translation or object recognition, and all the way to allowing us to communicate with our phones. And indeed, when you think about AI in the context of COVID-19, not surprisingly, you see AI systems at the front, helping scientists both to find vaccines and treatments to this disease, and as well as trying to make sense of all the huge amount of data that has been collected about this current pandemic. But perhaps aside from the great success that we've seen from AI, one thing that perhaps gets a bit unnoticed is that while models are becoming more and more accurate and allowing us to solve different tasks, they're becoming bigger and bigger. They consume, what you see here is a graph plotting the amount of computation used by state-of-the-art AI models between the years 2012 and 2018. And I think at this point, we're all used to seeing exponential graphs. So here's another one. We see a 300,000 times jump in the amount of computation required to train state-of-the-art models in 2012 to training them in 2018. And for those who think that this might be a trend that has plateaued to some extent, this is by far not the case, and we will see other examples from very recently that show that this trend still continues. So AI models are becoming bigger. They're becoming bigger and they're becoming more expensive. Expensive in terms of money, in terms of energy, in terms of other factors. And what we will be talking about today is this process of these models becoming bigger. We will start by describing something what we call red AI, which is the process of getting AI models bigger and bigger in order to improve performance. We'll talk a little bit about the background of how we got there and what are the conditions that resulted in models becoming bigger. We'll focus on two aspects: one, models becoming bigger, and the other, data sets becoming bigger, and show that these two combine to create a large price tag on AI experiments. And we will talk about the problems that arise from this, problems relating to lack of inclusiveness, to problems with adopting this technology, and to problems with the environment, which I will try to focus a little bit. I will then move to the second part, which we call green AI, which is a way to mitigate some of these concerns. We'll present two solutions. One is to focus more on efficiency rather than simply on the final accuracy number. And the other is to do enhanced reporting of computational budgets. I will explain all of this as we go on. And before I jump in, please feel free to stop me at any time. I can't see the chat, so if you want to say something, just jump in and I'll be happy to take questions throughout the talk. Okay, so let's begin with the first topic of red AI and see what we mean by that. So in order to understand what we mean by that, we will start by giving some background and talking about supervised learning, which is the basics of modern AI. In supervised learning, we have some sort of inputs, and we feed it to some machine, some black box that we will call we will call an AI machine, or AI model, and this model will output a label. For instance, we have the task of sentiment analysis, which is the task of predicting the sentiment of a given document. So in this case, we have a sentence like, "What a great presentation," and we would like our model to make a prediction of a positive sentiment. So let's jump a little bit into this middle part that we call the model, or this black box or gray box. And for our purposes, we can think of an AI model as simply a large set of numbers. We often call these numbers weights or parameters, and the process of an AI model working towards making some prediction is to perform computation over these weights, taking a bunch of weights here and multiplying by a bunch of weights there, and then some magic happens and we get, hopefully, the result that we want. And the process of getting the correct set of numbers into the model is called learning. This is the process of assigning values to the weights or parameters of the model. And when we talk about, so when we start the process, we have a model that contains numbers, but they're randomly generated. And then we run this process of learning that will take these randomly generated numbers and assign different values to them, so that, and again, so that this magic can happen and we were able to make accurate predictions. Now, in order to, how does this process happen? In order to assign these weights to the model, we need label data. We need basically examples that try to teach the model how to make the correct prediction. The model is basically learning how to imitate the training examples that it had seen, so that when it sees a new example, it will hopefully be able to generate a correct label. So when I say label data, I basically means pairs of documents and their labels. So we've seen the example of what a great presentation with a positive label. I didn't like that movie would get a negative label, and so on and so forth. So the process of learning, again, takes this set of label data, takes a randomly initialized black box that contains lots of numbers, lots of weights or parameters, and jointly using this set of labeled examples, fine-tunes these numbers, these weights in the model, so that the model will be able to make a correct prediction. And an important rule of thumb that we will be using throughout this talk is that the more weights a model has, the more data it needs in order to properly learn to make accurate predictions. We'll go back to this point later in this talk. Okay, so when we talk about supervised learning, the first approach that was used and worked well is often referred to as classical machine learning. This approach started to become popular in the mid-90s, and it had several characteristics. First and foremost, for our purposes, the models that people used were typically small, meaning that they had relatively few weights, and also the set of computations used by these models was also fairly simple. For instance, maybe one of the most popular classic model is called a linear model, where we take some vector that represents our inputs and multiply it by another vector of weights, and then we get a number, which we treat as our output label. This is a very simple model with a relatively small number of weights. An alternative to classical machine learning is deep learning. And in deep learning actually dates back to the early 1980s. And the key idea about deep learning is that, first of all, we're not using vectors, but more typically we're using matrices. And we're using multiple matrices, and we typically multiply them one by the other. So, and the notion of deep inside deep learning basically means that the more matrices we have when we're multiplying one by another, the deeper, quote unquote, our model is. So deep learning has a few nice properties. It has higher capacity than classical machine learning models, which allows us to potentially learn more accurate classifiers. Classifiers that will be able to handle a wider range of phenomena. At the same time, deep learning took quite a lot of time to get to work because the operations that are in the basis of deep learning, such as matrix multiplications, are typically slow on most hardware. And in addition, I remind you of the rule of thumb that we talked about just a couple of slides back, that the more weights a model has, the more data it needs in order to properly learn them. So it was quite challenging both to get a large enough amounts of data in order to properly train these models, and it was very, very slow. So it was all pretty hard to get these models to work. But then came two two interesting events that allow deep learning to become, to a large extent, what it is today. The first is relates to hardware, in particular, a piece of hardware called graphical processing unit, or GPU. The graphical processing units are devices that exist in every monitor and allow monitors to render the graphic displays properly. And interestingly, one of the key properties of GPUs is that they allow to do fast matrix multiplication. So in the mid-2000s, some people noticed that and started using GPUs as general purpose architectures rather than something to be used to generate displays. In particular, they use them to make the deep learning computations. And the second condition that's saturated roughly around that time is that crowdsourcing platforms starting to become popular. These are platforms such as Amazon Mechanical Turk and Crowdflower. And these are platforms that allow researchers and practitioners to collect large amounts of data in a cheap and fast way. The idea is quite simple. Say that I want to collect a large data set of, say, sentiment analysis. So I gather a bunch of documents, and then I reach out to random people on the web. I pay them a relatively small amount of money, and these people are looking for labor. Perhaps they live in places where labor is cheaper, so the amounts that I'm able to pay them are hopefully satisfactory. And because there are so many people like this around the world, I get back my labeled documents in, again, quite fast and in a non-expensive way. So now we have these two conditions. Now we have matrix multiplication operations that can be performed pretty fast, and we have a way to collect large amounts of data. And when these two conditions were met, we came to the moment that changed history for the field of AI, which is the ImageNet competition in 2012. Now, the ImageNet competition is a typical competition in the computer vision community where the goal is quite simple, given an image, to recognize which object appears in that image. So we can have images of dogs, or particular dogs like huskies, or sailboats, or what have you. And researchers and practitioners from around the world are trying to build systems that better identify which object they're currently getting as input. And this competition was not new at the time. It's been around for several years, and every year a new machine would come out that would improve the results over the previous year by, say, a fraction of a percent, maybe 1/4% or 0.5%, and kind of progress was going quite slow. And then in 2012 came a group of researchers from the University of Toronto, and they presented the following results. So what we're seeing here is a table that shows the performance of, on the first row, the best classical machine learning model. So on the right-hand column, you see the proportion of errors that this model had made. So this means that basically out of every 100 images that we show this classical machine learning model, it would make mistakes in about 26% of them. And the bottom line shows the best model presented by this Canadian group, which they called AlexNet, and was based on deep learning. And this model, instead of getting 26% of the answers wrong, they got about 15% of the answers wrong. Now, this was an amazing breakthrough, something that the computer vision and the AI community as a whole has rarely ever seen something like this, such a huge improvement. And for me, I'm a person who likes sports, and I like to find analogies between large events that influence a complete field. And I think of the 2009 athletic world champions, where Usain Bolt broke the world record from 9.69 to 9.58, which was I believe, the largest or one of the largest improvements in 100 meters world records. Or you can think of Steph Curry scoring 54 points and 11 three-pointers in a game against the Knicks in 2012 and 13, which to a large extent changed the way basketball is being played in the NBA nowadays. So again, ever since 2012, this moment, deep learning basically took over. the entire field of AI, whether it is computer vision, speech recognition, natural language processing, and so on and so forth. And maybe one of the key elements that we see in deep learning models is that they scale very, very well. What do I mean by scale? It means that basically, if you have, I remind you that we're talking about deep learning models, we're talking about a series of matrix multiplications. So if we have a matrix that contains a bunch of numbers, we call these numbers parameters or weights, I remind you, we can simply take it and make it wider, basically use a larger matrix with more numbers. And basically, this is a very simple way that will probably result in a more accurate model. And similarly, we can take a deep learning model that is deep in the sense that we're multiplying multiple matrices and simply make it deeper, basically multiplying more of these matrices. And the end result is that something that we now call one property of red AI is that models are becoming bigger. Models, they have more weights, they perform more computations, and so it's become more and more expensive to train and to run a deep learning model. But let me remind you that it is not enough to increase the size of datasets. We have this argument that we've seen a couple of times already in this talk, is that the more weights a model has, the more data it needs. So indeed, we've seen, in addition to models becoming bigger, we've seen, and because they're becoming bigger, they're becoming more hungry, quote unquote, for data. So we've seen large data sets being released of tens of thousands, or even hundreds of thousands, or even in some cases, millions of examples. So now we have the second condition to red AI. We have models that are becoming bigger and bigger because AI models or deep learning models scale very well. And we have a platform to collect large data sets that allow us to create larger data sets. So the overall price of generating and using AI models is becoming more and more intense. Now, before I continue, this might be a good time to stop for any questions if anybody, if anything is unclear or. Okay, I'm not hearing any questions. Please feel free to jump in if there's anything. Okay, so we've seen the deep learning models becoming bigger and datasets becoming bigger, but at a certain point, we've reached some sort of plateau with respect to the size of datasets. We've seen datasets reach to hundreds of thousands, or in some cases even a small number of million of examples. But it's very hard using crowdsourcing platforms for models to scale, for dataset to scale. Sorry. Excuse me for a second. Sorry. So perhaps the next step in making AI's models even more accurate was to generate sources of naturally occurring supervision. Sorry. Basically getting supervised labels that do not require people to actually write them down. And this is to achieve that, several researchers approach the task of language modeling. Language modeling is one of the key tasks in natural language processing, and this task is quite straightforward. Given a sentence, like the boy read the goal is to complete the sentence with plausible continuations. For instance, we might see things like book and story, but we will probably not see things like giraffe or the or apple. Similarly, if we have something like the presentation is, we might see things like interesting, funny, or maybe boring or long, but we'll probably not see things like tree or paper or tall. And the key idea about language modeling is that it doesn't require manual annotation. Basically, you can take any sentence that you find on the web, and as you all know, there are lots of sentences on the web. And every sentence becomes a new training example, because you can take the sentence, drop the word, and ask the model to guess which word you dropped. So in this sense, dataset size now also scales, because we can use all the data in the internet for that matter. And some models have practically done that recently. So we can grow our datasets much larger. So a group of researchers from the Allen Institute for AI used this idea to perform what many think of as the third deep learning revolution. The idea was as following. They started by training a large language model, a language model with 100 million parameters, and that was trained on a huge data set of 1 billion words. And now they had a language model that works pretty well. And now you wanted to do another task, a task like sentiment analysis. Now, I remind you, for sentiment analysis, the task of predicting what is the sentiment of a given document, you need manual labels. So you can't collect 1 billion examples like that. This just doesn't scale that well. But what they did was to take the same network that they trained for the language model, add a small piece of a new network around on top of it that contains a small number of parameters, so it doesn't need much data. And now they have a new method, a new model to perform sentiment analysis. And interestingly, if we had this concept of the more weights the model has, the more data it needs, now we have a very, very big model that doesn't need that much sentiment analysis data. It can settle for maybe hundreds or thousands of examples rather than millions or billions of them. And indeed, this idea, the authors called it ELMO, became completely swept the field of natural language processing off its feet. They tried, here you see an example from the original paper where they tried it on 6 core NLP tasks. And in every single task, this approach led to significant improvements and to a new state-of-the-art result. Now, to better appreciate what we're seeing here, in standard papers in AI, we typically see an improvement in maybe 1 or 2 tasks, maybe 3 tasks if the authors do the work really, really well. But here we've seen 6 results in a single paper that was reproduced to basically every single task you can think of. Using this method resulted in a gain in accuracy. And again, going back to to give some perspective to these results, I like to think of it as a moment similar to the Beijing Summer Olympics in 2008, where Michael Phelps won 8 gold medals. Basically, every competition that he participated in, he won first place. And this is roughly what ELMO did to the NLP community. So with the revolution that ELMO started, just completely changed the way we do NLP nowadays, and AI to a large extent. Because we're seeing models just keep getting larger and larger, and because we can use larger models, again, we can just make our matrices larger, we can multiply more of them, and so on. And we can gather as much data as we want to compensate for this a large number of weights. And so indeed, what we're seeing here is a graph that shows the ELMO is the leftmost point. On the right-hand side, we see a model released about a year and a half ago from Microsoft called TNLG. And ELMO had about 100 million parameters, and TNLG had 17 billion parameters. So in about 2 years, we've seen 170 times more parameters for the biggest NLP model. But that's not the end, actually. This was about 1.5 years ago. And in mid-2020, about a year back, OpenAI, an organization in California, released a model 10 times bigger. So 1,700 times in 2.5 years. And just a few months ago, Google released a new model that had 1 trillion parameters. So 10,000 times in 3 years. This is the exponential jump that we've seen thanks to the introduction of this method by folks at AI2. And not surprisingly, as we said, we need, as our model size grows, we need more data as well. And indeed, when we see the number of words used to train state-of-the-art NLP models, we see a 100,000 times jump in 3 years. And again, there's no end in sight to any of these trends. So if we take a step back and we look at what do we think about AI, red AI, we talked about models becoming bigger and dataset becoming larger. And now actually we're not talking about big and large, we're talking about huge and extra large. We're seeing models becoming tremendously large and tremendously expensive. Any questions so far, or any thoughts on any of this?
Yes, I have a question.
Yeah, sure.
So I'm wondering, I mean, of course, this is mostly tech companies investing in this and training these large models. But is it somehow feasible for them, or what if there's so much energy consumption and money and resources involved? What's maybe the motivation to still invest that much? Is it feasible?
That's a great question. So the question was, if I understand correctly, whether given, I mean, I haven't talked explicitly. I think my next slide is about the money cost and then next the energy cost of this process. But you're definitely correct that the only players that can afford to run these experiments are huge companies that have very large revenues. Then they can afford to invest in some cases. I think this is indeed the next slide. We see some examples of numbers that these models cost. So the most recent model that we've seen from OpenAI called GPT-3 cost to some estimates say $12 million. And so these companies, I don't work in any of these companies, so can only speculate. But I think when you think of the potential revenue that these companies get by getting more accurate AI systems, it's probably worth for them to make these investments. In terms of the energy and carbon, this is one of the key issues I think here that maybe they're maybe not penalized enough for making these generating these amounts of CO2. But yeah, when you think of a company like Google or Microsoft that are running these experiments, even $12 million, it sounds like a fantastic amount to a regular person. For them, it's probably not that much.
All right. Yeah. Thanks.
Yep. Any other questions or comments? Okay. So let's continue. So indeed, models are becoming more and more expensive, up to, again, the millions of dollars to train just a single model. And this creates several problems. So let's dive a little bit about following the question that was just asked. I think the first question to talk about is again, given that these models are so big and so expensive to generate, very few players can afford to do that. I myself don't have $12 million to invest in a single experiment, and not sure that I would like to, even if I had that amount of money, but that's a different question. So at the end of the day, we're seeing that only a small number of players are able to basically set the agenda on what gets studied, what kind of data is being used to train these models. What does the data contain? Does it contain biases? Or does it contain foul language or what have you? And this is creating a serious challenge for the AI community. A second problem that does not involve the community itself, but maybe the customers that use it, is that these models are so huge and it's very hard to deploy them in servers or on phones or on laptops or what have you. And it might be a question of not only who gets to decide which models get created, but who gets to use them. If you're a small startup that doesn't have a large enough capacity in your systems for these models, you might not benefit from the fruits of this research. And finally, perhaps most related to this session, big models consume a lot of energy. And here is one recent study by folks at University of Massachusetts, led by Emma Strubel. And they compared one of the largest NLP experiments a couple of years back. They computed the amount of CO2 omitted by this experiment and estimated it and compared it to, on average, CO2 omitted by a car during its lifetime. And what they showed is that this model omitted 5 times more than or basically equivalent to 5 cars in the course of their lifetimes, which seems pretty significant for a single experiment. And of course, this is a result from 2019. So and the field has not, as we've seen, has not stopped generating larger and larger experiments ever since. So I want to talk a little bit about the cost of AI experiments in terms of the environment. So we have evidence about some evidence about the most expensive experiments. those that are run only a handful of times, and we see maybe a rough estimate that they consume the same amount of energy as a car would in the course of its lifetime, or several cars would in the course of their lifetime. And you can argue whether this is a reasonable price to pay. Maybe if we're generating a tool that we're only running this experiment several times, maybe it's worth it. But some things that are perhaps under-discussed are, what about other experiments that are not the most expensive ones, but are not run once or a handful of times every year, but are run hundreds of times or thousands of times a day by researchers all around the world? How much do these experiments cost, and what is the total aggregate of the AI industry? And finally, when we talk about perhaps the cheapest operations of inference operation, of taking an AI model that someone already built and just using it to make a prediction, again, this is a very, very cheap operation compared to the operations that we've seen before, but still becoming more and more expensive because the models are still getting bigger. But these operations are run perhaps billions of times a day. If you think of how many Google search queries, or how many Microsoft translation queries, or how many Amazon product recommendations are generated every second, these numbers are enormous. So perhaps, and much harder to estimate based on the large number of locations and companies that run them. And indeed, when we some estimates talk about the AI computation, global computation budget is that say that 80 to 90% of this budget goes to inference. So perhaps the key point here is that it's very hard to measure, as the only evidence we have that we're basically scratching the surface, and we're seeing that some experiments are very, very environmentally impactful, but we don't know enough about the rest of the experiments that are potentially much more intensive. Okay, so taking a step back, we talked about the concept of red AI, of models becoming bigger and of datasets becoming larger. We talked about how we got to the situation where this is what's happening and what's the motivation behind it. We talked about various problems that we see with this trend, including problems with inclusiveness, problems with adoption, and problems with the environment. And I want to present a couple of ways forward. We released an opinion piece about a year ago titled Green AI, which outlined these problems and tried to present ways to mitigate some of them. So let's talk about this. And before we move to the problem, to our solutions, I want to emphasize that we do not want to eliminate red AI experiments, these large experiments. They are very important in the sense that they are allowing us to push the state of the art. And in many cases, when one organization trains a very large model, many other organizations can afford to use it because, without investing their own money, because the original organization publicly released it. So there's lots of values in training these large models, but at the same time, as we've seen, there's also concerning side effects with respect to inclusiveness, adoption, and the environment. So our goal is to mitigate these side effects, not necessarily to stop training in these large models, but to try to think of ways to mitigate the relevant negative effects of them. So the first thing that we're proposing is to put more emphasis on efficiency rather than on accuracy. Now, efficiency is one of the core components of computer science, so it feels almost trivial to be discussing it. But when you look at, we did a survey of 20 top papers from the 3 most influential conferences in AI, in natural language processing and machine learning and in computer vision. And we took 20 random papers and we checked whether their main contribution was improving some measure of accuracy, improving some measure of efficiency, or none of the above, or both of them. And we found in all 3 conferences, the majority, or even the great majority of papers focused on accuracy, and very few papers focused on efficiency. And we think that this is not as a balanced approach, and we believe that things should be a little more adjusted. and more effort should be made towards making models more efficient in order to reduce these costs. The second idea that we propose is to do better comparison between models. What do I mean by that? A typical AI paper will generally introduce a new model, let's call this model A, and run it against some baseline, which is a previous approach that someone else created, and argue that their model is better because their accuracy is better. And what we're trying to propose is, instead of saying that model A is better than model B, say that model A is better than model B given some budget constraint. And I think this makes much more sense because if model A is better than model B just because it's using 10 times more compute, then this conclusion is perhaps not scientifically valid. And we propose in particular to report not only a single result with a single budget, but perhaps a range of results with a wider range of budgets, which would make comparison between models much clearer. So a new practitioner would know if they have they want to take one of these models and apply it to their own needs, but they know that they have a small budget, so they might want to make a different decision than a parallel researcher or practitioner that has a larger budget. So again, what you see here is an illustration of our approach. On the x-axis, you see some measure of budget, say how much time you have to run you can afford to run your model. And on the x-axis, you see how accurate your model is. And here you see that on the brown line is better on small budgets, while the blue line is better on high budgets. So and again, if you like analogies, on the right-hand side, you see here Yarden Jerbi, which is Israeli judoka that won the bronze medal in the 2016 Summer Olympics. And on the left-hand side, you have Emilie Amdeol, who won the gold medal in the same Olympics. But obviously, these two judoka did not compete one against each other because they are different weight classes. And it wouldn't make much sense to have them compete against each other. So in the same sense, maybe it makes more sense for AI models to compete on a similar budget. And why is this important and related to the concept of green AI? Because we think that once people start paying more attention to how much budget is required to train a given model, others will try to compete on minimizing these budgets and getting better results on a given budget. So before I wrap up, I want to talk a little bit about what happened since we published this paper about a year back. We started seeing some encouraging initial results. First of all, within our AI community, we've seen major AI conferences allowing special tracks to submit efficient or green work. Basically, allowing researchers that have great ideas about how to make models, say, more efficient or how to do better reporting, a place to publish in the top tier conferences, which wasn't necessarily the case beforehand. Secondly, we saw a new wave of workshops that focus on sustainability and efficiency. Again, workshops are dedicated venues for a particular topic. So we see more and more efforts towards sustainability and efficiency. And finally, we've seen efforts towards making AI scientific publications more reproducible. Basically asking authors explicitly to report things, including their computational budgets, which again is one of our major goals. And we also saw a great interest from the general public with pieces in the New York Times, MIT Tech Review, and others that all try to recognize these concerns and try to help us think about ways to promote them and to educate the general public about it. And related or unrelated, we've seen that in parallel to these two efforts, large players are starting to notice. For instance, the GPT-3 paper that we mentioned a couple of times, a model that had 175 billion parameters, had a section about energy usage in their paper, which did not appear in previous similar publications. And actually, just two weeks back, Google released a paper titled Carbon Emissions and Large Neural Network Training that tries to estimate the amount of CO2 released by their models. So with that, I think I will stop to quickly summarize what we've talked about. We talked about the concept of red AI, of models becoming larger and effectively and correspondingly data sets becoming larger and larger. And we talked about how we got there, the various deep learning revolutions. We talked about problems that it creates with inclusiveness, adoption, and the environment. And then we presented our solution, or a partial solution at least, of green AI, of enhancing activity on efficiency and of reporting. So with that, I will end, and I want to thank you for your attention, and I'm happy to take questions.
So is it okay if we could just ask questions via voice chat, or should we ask them in the chat?
I can't see the chat, so if you can ask and use your voice, that will be simpler for me.
Okay, then I'll just raise one question here. Thank you for the talk, first of all. Very interesting insight. So we were recently trying to certify machine learning models by also discussing their resource consumption, runtime, and all of that. And we found it very hard to come up with a way to measure the resource consumption, like explicitly. Of course, you can just measure the energy of your computer multiplied by time, and then you can kind of identify that. But internal measurements are really hard to do, like profiling GPU usage, energy draw, or something like that. Have you ever so do you know if there's something in work that makes that a little bit better comparable?
You're asking a great question. I think so. I have a few things to say here. First of all, I consider it one of the biggest open questions that we have nowadays. What's the right way to report energy consumption? I mean, again, there's so many things to measure. There's the runtime, there's the amount of energy, there's the amount of money on the cloud, perhaps. There's so many things that you can try to measure. We, in our paper, propose to measure the amount of floating point operations that are being used to run the system. This basically means how much operations are being used by the system. And this is not a perfect, very far from being perfect, but it has a nice benefits that it is comparable between different researchers around the globe. And it is independent of your electricity infrastructure and the time of day and so on and so forth. If you want to measure carbon specifically, there are various tools that have been released in the past year or so that try to estimate the amount of carbon. I can share links. I'm not sure how exactly, but I can send the organizers some links if this is helpful. And again, these tools are a good starting point. They're still rough estimates, I would say, rather than accurate numbers. But again, this is a very important open question, and we're still working on it, to be honest.
Thank you.
Yeah,
I would also
maybe,
have a.
okay.
Go ahead. Go ahead.
Okay, yeah, thank you. First of all, thanks for the nice talk. I have one question. So I think in today's leaders, we have leaderboards, right? And with these pre-trained models, we get high accuracies. So, but like you mentioned that these pre-trained models, they are in some way also having effect on our environment. So what do you think like the community should do to basically create a parallel balance between having high accuracies on leaderboards as well, but also not affecting the environment?
That's another great question. You're asking all the right questions, I think. We've been thinking about various ways to tackle these problems. I mean, there has been a few initiatives recently that try to come up with leaderboards that take computational budget into account. There was a recent efforts in Europe to devise question answering system that has a limit on the amount of time that it can run or the amount of parameters that they are allowed to use. And so this is one way of tackling this problem of kind of introducing alternative leaderboards that do take budget into account. I think public pressure is always helpful to raise awareness of these problems. I'm pretty sure that I think most of the AI researchers that I know care about the environment and don't like to do things that are harmful for ourselves and for our children's future. But at the same time, it's hard to take these things into account in your day-to-day work. And I think perhaps bringing this topic into awareness and making people think about it is another important way forward. And this is basically the way we're trying to promote things via trying to talk to the community, to educate the community, to adopt better practices in this sense. I hope this was in some way helpful.
Yeah, thank you.
Thank you. I also have one question. I don't know if we still have time, but you also have here for the red AI the inclusiveness, so the social part, let's say the social sustainability part, I would say. But isn't there also like some conflicts? Because like I've seen some preliminary research that shows the first thing that bigger networks forget are the very underrepresented cases or the seldom cases in the data set. So then you may have more efficient models, but then have an increase in the sort of social bias. I don't know, do you see this as a big problem, or what's your take on that?
Another interesting and great question. Well, actually, when you initially thought about talking about trade-offs, I mean, one can say that if there wasn't any problem of inclusiveness in terms of everybody had access to unlimited amount of resources, would probably have a much higher impact on the environment. So maybe it's good that not so many people have access to these computational budgets. But I think basically, but that wasn't the question you were asking. I think this is an important topic, and kind of the question is when you make a model smaller and more efficient, how do you get away with losing information that is redundant rather than forgetting, say, the long tail that maybe influences less but potentially contains information about underrepresented groups. This is a great question. I mean, it's very. I definitely don't have the solution, but I think. I have students that are actively working on thinking about similar issues and trying to think about. They're actually thinking. I mean, when is it helpful to forget information? When you think of, perhaps if you think about gender bias, when you think about say that pilots are typically male and flight attendants are typically female. So you want the model to forget this part of information so that it doesn't make this implicit assumption that pilots have to be men. But you might be asking the right questions, and maybe they're losing information that does marginalize certain groups. These are all great questions. Again, no solutions yet, unfortunately, but I can promise you that we're working on this. Okay, I think if there's no more questions, if somebody wants to reach out, please feel free to email me. I'm happy to continue this discussion offline. So thank you again for your attention.
Thank you very much.